Okay. Okay, thank you for a very kind introduction. I will be actually the first one who will be presenting in person here, so I hope you find it more interesting and easier to follow. So, like was introduced, I'm Joseph Kwon. Korean name is Sang-il Kwon, and I am with Texas A&M, but actually now I am on my sabbatical at KAIST. So I was here since June, so I think it will be a great honor to have this opportunity to share my work on quantum dot. So my background is more on the multi-scale modeling and control of different applications, and quantum dot is actually one of my favorite applications, because my PhD thesis was about the pharmaceutical. I know that many of you were talking about microfluidics or tubular reactors and so on and so forth. So I actually developed like end-to-end, I would say, unified modeling and control framework to enhance the productivity of a pharmaceutical manufacturing process. So, and then I found that the similar approach can be expanded to the quantum dot manufacturing. So by collaborating with, because I'm not doing any experiments, so I had to find collaborators. So by collaborating with the many excellent professors in the States as well as in the Korea, I was able to actually work in this area. So with that, this is the brief outline of my talk, and let me first start with the background. So I know that the session title is more like biomedical, while I'll be more talking about the quantum dot. But I found that since I will be also talking about the microfluidic kind of component in this work, so I hope maybe that is relevant to the previous work. So QDs, or quantum dots, are indeed nanocrystals, which is typically in the range of 5 to 10 nanometer, so it's very small. And then there are a few very widely considered quantum dot variants, and then one of them, I mean, probably the one that most popular is the second one, the session-led, the halide. And you know, since it's halide, so it can be many different things, but I think in this work I'll be primarily focusing on the session-led bromide. So the reason why it's very popular is because it has a very high the photoluminescence quantum yield, which is in short the PLQY, and I mean, because of which it can be used in many different applications. I mean, some people, I mean, because you know, I know that every time we go to like some general conferences, there are actually a number of people who are presenting their work on quantum dots. So I think you may have some impression that the field itself is quite mature, but it's not the case. It's still, even though there has been a lot of work done recently, but there's still quite a bit of work, I mean, more work to be done. And then there are a lot of ongoing effort in these directions. But so I found this is a very futuristic, and then I think this is very timely. So with that very high PLQI, while we can do many things, but before we talk about it, also another thing that you may want to pay attention is that when every time people say QD, it comes with something called a quantum confinement, which basically means that the size of QDs are so small, and then you can basically control the band gap. So like what I mean by that is that if you basically see this small cartoon, then you see that the particles of a size of, say, 5 nanometer, it will emit more like blue colors when it was irradiated with a UV. On the other hand, I mean, the relatively larger size, like quantum dots, it will emit the red color. So how that is relevant to our daily lives. So this high luminosity and the monochromaticity makes QDs ideal for particularly like displays. So I'm sure we use a QLED TV in these days, and I mean, the reason being that the high resolution LED the blocks of RGB QD particles are utilized because of the high luminescence. But the one thing is that I mean, although I'll talk about this in detail, but actually the size matters. So it requires like very fine tuning of the size, but that particular part is not very mature yet. And in addition to its kind of great applications to displays, also it can be used for the manufacturing of a solar cell. So I mean, silicon-based solar cell have been widely used, but of course it actually requires quite severe crystallization conditions. But actually this quantum dot, it requires relatively milder conditions. And also there are a lot of like jargons like the exciton formations and QDSC and then, I mean, many things. But I think the one take-home message that you may want to remember is that QDs can be used for manufacturing of, producing display, nice display, high like resolution display, as well as it can be used for manufacturing of a solar cell. So initially I was going to actually break my entire talk into these two parts. So the first one is that, well, so we have a very nice applications, then how can we actually manufacture those QDs, and then how can we actually apply or use it for manufacturing solar cell, because each one of them has a very interesting modeling and control needs. But then I think considering the audience and so on, I thought it would be better to just focus on how I can manufacture the QDs. So this is what I'll mainly talk about today. And in terms of the market growth, the QD display market will reach 2 billion in 2025, with Asia leading the growth. I mean, here Asia means Korea, China, and India. So, I mean, as you can see, the annual growth rate is about 60%, starting from 2019. This kind of expectation, but it's really huge. And also, so this is more like the QD market itself, but if we take a look at more specifically the QD-based solar cells, like again, I mean, you see that the annual growth rate over these few days, few years, few next years, expected to be quite high. So that's why it's a very kind of preferred approach these days. And I mean, like I pointed out, it does not require extreme conditions, unlike silicon-based solar cells. So I mean, there's another advantage of using QD-based solar cells. So with all these nice things, and then the ongoing effort, and then recent trend, now let me move on to the key issues and challenges associated with it. So and then these are kind of like from the standpoint of like modelers or the process control engineers. So first of all, in general, like not like QDs, but in general, like organic or inorganic, like crystallization process, like sugar, like maybe even proteins and so on. It actually requires a lot of time to actually see the onset, and then it actually, I mean, if you run kind of batch process, it actually takes maybe like more than 10 hours, or sometimes like very close to like a day or something. But QD crystallization, I think one of the biggest differences is that it's a very, very fast. So it takes about, I don't know, 30 seconds. I mean, actually the example, the case study that I'll be talking about today is actually less than 30 seconds to minutes. So it's making it quite difficult to study the mechanism and basically kinetics. So there are actually many different ways to synthesize it. So I mean, like when you talk to like a different kind of group of people, that they may have a different schools of thought. Like say, I mean, one may use like hot injection method, and then some others may use a different method. So that's, in my view, I think one of the great obstacles in terms of like developing like kinetics, because depending on like different synthesizing approach, it will definitely affect like the underlying kinetics. So I think we first have to find like the consensus between like different approaches. But since I'm not a experimental people, so that's not my job, but what I will be doing and then I will be presenting today is more like compare different approaches and then see which one would be the most appropriate one. So, okay, so that was the first one, and then the second approach. So like the first issue is more like I would say developing a kinetics or finding a kinetics of a QDs. But the second challenge is that a lot of a QD synthesis is primarily done in lab scale, or like I would say maybe flask-based scale. So as you can see, it's quite from the standpoint of like process engineers, it's like very small scale. Okay, so quite far from the mass production. So because of which there will be a batch-to-batch variations, which has to be modeled, but it's not easy to model using some like deterministic approach. And also, given the quick process time or the very fast like nucleation rate, it's not easy to control the QDs. So I mean, these two are quite a bit of like challenges if you were to develop like a continuous time or the mass production of these QDs. So I think even though there have been some work trying to increase the throughput by developing different approaches or even using the tubular reactors and so on, but primarily the approach focuses on black box models. So like what I mean by black box here is that they do not utilize any first principles here. Instead, they just like use the data and then trying to develop like a data-driven approach, and based on which they either design a controller or solve optimal operation problems. So I found that there's another kind of key challenge here. So in summary, for QD manufacturing, finding a QD crystallization growth kinetics for effective modeling and control of a fast, scalable manufacturing of QDs, I found that it is one of the key challenges. So in order to address this challenge, I took the following 5 kind of steps, and then I called it like more like multifaceted QD modeling framework. So it will primarily consist of the microscopic models, which will focus on describing the QD crystal growth, and the microscopic modeling, which is more like a reactor scale or like crystallizer the level. And the multi-scale model will combine these two to better describe the interactions between these two different scales. And the surrogate model will be developed because the multi-scale model will be quite computationally demanding, and then you cannot directly use it for finding the optimal operating conditions and so on and so forth. So this is why we actually have to use like a surrogate model, and then that will be directly integrated into the optimal control framework to regulate the crystal size. So with that, we have one collaborators at North Carolina State University. The professor Milad Abul-Hassani, and then Robert was, I think, one of his recent graduates. So they kind of developed a very nice experimental setup to enable the continuous production of QDs. So I think the total length is about 1 meter, and then it's like, he intended to say like milli-fluidic. Okay, so I will just like adopt his expressions there. And then I think the good thing is that they will produce, so basically like once they inject like a small seeded like nanocrystals, which is nothing but QDs, then like they will grow all the way, like as they travel along the this like crystallization reactor, which is about like 1 meter, and then once they'll first measure the light intensity, and then because they have already constructed like kind of like lookup tables, so they can try to calculate the corresponding crystal size and so on and so forth. So basically through that kind of like sequential approach, we were able to have like a real-time kind of measurement of the crystal size while they are growing. So what we are trying to do is like we mimicked their reactors by developing some like digital twin, and then we divide them into like like multiple partitions, and then we basically first came up with this like a reactor scale model. So the first equation is for the concentrations, which involves all the necessary terms, and the second one is how the temperature changes with time. And then you see that there's this like a growth rate terms, which has to be provided by us because we were in charge of the modeling. But then I think one of the problem is that as you can see here, actually this is like I think it's the lysozyme, the protein crystallization. So you see that for any mature crystals, I mean like mature in a sense that there have been a lot of work done, and then lysozyme is one of them. You can actually find many empirical growth rate relationship, but the problem is that here, particularly for QDs, there are not many fundamentally correct and then reach some consensus by a lot of different researchers. Like there are no such kinetic models for QDs. So what we were trying to do is like we're trying to calculate the growth rate starting from scratch by using something called the kinetic Monte Carlo simulations. So we primarily used something called a solid and solid, like a lattice model, which basically means the solid will be stacked in this very tight and compact manner, so there will be no dangling bonds, and then there will be no like porosities and so on and so forth. So the particular the lattice site were used to calculate the crystal growth, and then also we kind of run the multiple chem simulations to describe the size evolution of a crystal ensemble. So I mean, like rather than assuming that all the crystals will follow exactly the same size and shape value, we consider, because I mean in reality, like there will be a distribution of size and shape. So this is what we were able to actually mimic or calculate using the chem simulation. So in order to kind of present a little bit of details of how the chem simulation work in case that you don't have much background about chem simulation. So the Monte Carlo simulation in general is based on the probability. So I mean, based on the probability in case of equilibrium Monte Carlo or just Monte Carlo itself. So this is more like calculating the, let's say, thermodynamic equilibrium of a system. So it's more like finding a solution of algebra equations. However, so I mean, like this is the reason why it was particularly useful for steady-state calculations or equilibrium process. But in case of kinetic Monte Carlo simulation, since we have this word kinetic, that is mainly for the non-equilibrium processes like crystallization process. So crystallization process is actually non-equilibrium process because when it reaches equilibrium, that means like there's no, I mean the supersaturation level is very low and then nothing will happen. So basically like throughout the entire crystallization process, we want to make sure that the system never reaches like equilibrium. I mean that's why this is like a non-equilibrium process. So for the non-equilibrium process, like you see that, I mean, and then also crystallizations there are actually a group of a lot of different systems where like surface configuration matters. So like for example, like some particles can deposit on the surface and some particles will kind of like wandering around, like they're like migration event, or some of them can like aggregate with each other, or some of them can be dissolved from the surface. So in such cases, we can use kinetic Monte Carlo simulations to kind of like consider all of like different events in the simultaneously. And how? We can actually do that by taking into account like some approaches called like metropolis, or more specifically speaking like a Gillespie algorithm. So the idea is that suppose there are like 10 different event order reactions, and then each one of them will have like different reaction rate. Then if you think about like them in a more like continuum scale, then you view that they are competing with each other, and it's possible that they will all can occur at the same time. But in reality, if the numbers are not close to like like Avogadro's numbers or something, then we can actually consider them in a more like discrete manner. So the idea is that like you will compare which event will take place within next like whatever sampling time, and then you assume that the probability that the particular event will occur is proportional to the reaction rate of the particular event. I mean, like, which makes sense, right? Because if the reaction rate of one reaction is much faster than the other, then it's more likely that that event would occur maybe like 10 times or 20 times or like more. So that is the idea. And the second thing is that since the chem simulation is by nature like stochastic algorithm, so it can actually mimic like like a variability like batch to batch or like surface to surface or event to event variability inherently. So this is why in general we'll consider like an average of like 10 to maybe 50 kinematic simulations to represent the true dynamics of the systems. So in this work we actually, because I think there are two schools of thought in terms of how crystals grow. So the first one is that I call it like the mechanism A, which is like formation of a bromine shell on the crystal surface. So it basically, I mean, the idea is that it is based on the hypothesis that a bromine shell hinders the crystal growth, resulting in a size control of the QDs, and then we have one collaborator who actually observed the behavior. So in this case, I mean, we can consider like a different rate laws for adsorption, desorption, migrations of session-led the bromide unit cells, and then we did it, and then that particular work is published here. And then another school of thought is formation of a ligand shell on crystal surfaces. So according to some literatures, they proposed that there will be ligand form a shell on the crystal surface, and it can be actually helping like some precursors to kind of like transport all the way to the surface, and because of which like the crystal will grow. So basically these two approaches kind of requires a little bit of different modeling like effort. So we kind of compared which one actually provides a better like a result. So according to the first approach, like mechanism A, we compared our simulation result with experimental data, and then you see like there's some deviation. So like we developed the model and they provide the same initial conditions that to both, and then we see that there was a deviation. On the other hand, when we follow the mechanism B, which is based on like a ligand shell on the crystal surface, we found that even at a different like a flow velocity, the simulation result and the crystal simulation result and the experimental result were quite aligned well with each other. And particularly, this was more like batch, and this was for the tubular reactors that we collaborated with the professor at North Carolina State University. So I think once that kinematic simulation was constructed, we kind of integrated with the tubular crystallizer model, so that you see that we had that crystallizer model, which was primarily based on the mass and energy balance equation. So we integrated the kinematic simulation so that we can describe not only the concentration and temperature profile along the tubular reactors, but also how each crystals, as well as the surface of the crystals, like changes over time. So if you take a look at this crystal size distribution along the tubular reactor lengths, as well as the time, this is the profile that we obtained. And so, with that, what would be the next step? So, because, as I mentioned, the size of QDs are quite important, because all the important properties would actually be dependent on the size of the QD. So, the size tuning is very necessary. And then, since we have this model, what we can do is we can utilize this model to find the optimal input and process conditions to achieve the desired the QD size. So, in this work, we actually use like a feedback control. We wanted to use the feedback control, but the problem is that typically the feedback control can be done in every like a minute or like 5 minutes or even 10 minutes. Depending on the sensors and the actuator you have. But the problem is that the entire kinetics or the entire growth of the QDs will be finished within 10 seconds or 20 seconds. So we were not able to actually do such a very fast control. So instead, what we did was we utilized a model and then tried to calculate the inlet concentration and the inlet flow rate by solving an optimization problem. So we constructed the optimal operation problem as follows, which is like nonlinear optimization problem, where we can find the optimal input concentration as well as the flow rate. So you see that these are the parameters to be obtained, which is the inlet concentration and the inlet flow rate, to minimize the crystal size at the end at the exit of the tubular reactors from its the set point. And then we also want to minimize like not providing too much like concentration and then not varying the flow rate too often and something like that. And then these are actually like the high fidelity like multi-scale model that we developed. But the problem is that the model itself, because it has to integrate both the crystallization model and then kinetic Monte Carlo simulation, so it actually takes quite a bit of time to solve it. And also the problem is that with this optimization problem, you will solve it at least like 100 times or even more times of iterations to find the optimal solution. So the problem is that we probably need to replace this computationally very expensive part with computationally affordable one. And then in that regard, we replace it with the artificial neural network. So since we already have a lot of data from our the multi-scale high fidelity model, where we were able to vary like inlet concentrations and the different flow rate, and then we were able to obtain the crystal size at different locations at the end of the exit of the tubular reactor. So we have all this data, and then we fed them into the artificial neural network to find the computationally efficient like surrogate model. And then as you can see, like the difference between the actual kinetic simulations and then they obtained the computationally efficient artificial neural network was like very close to each other. So we were happy with it, and then we decided to move on. So if you compare how much time it requires to solve this A&M versus KM simulations, we were able to improve the speed boost by 24,000 times. So in the end, we solved the optimization problem, and then as you can see, our QD size, we were able to kind of like regulate to like desired size. And the reason why we have this kind of a light color is because our model was also able to provide a distribution of a QD size. So to make long story short, this is not like closed loop control approach, but an open loop, because we were not able to have the timely control of this. Real-time control of this particular system, because it only takes about 10 seconds to complete all the process. So, okay. So now to conclude. So there's a few issues. So the first issue was that there's no comprehensive high fidelity crystallization model, and the second issue was that there were no modeling and control framework for enabling the continuous QD manufacturing. That's why, in order to address this key challenge, we developed this unified framework, and then which is presented right here. And then I want to particularly appreciate many collaborators at North Carolina State University and Sogang University, as well as my own institution, Texas A&M, and then all of this work was done by Niranjan, who's a 5th year PhD students. So with that, I want to conclude my talk, and then we'll be more than happy to take any questions you have.
Thank you, Professor Won. Any questions from the audience? I have a quick question before we move. Based on your kinetic Monte Carlo simulations, do you think that it might be feasible to experimentally construct a system where we can tap to collect size-specific QD crystals, just like a distillation tower design?
I think there's something we can do, but so like I said, once we fix the length of say tubular reactors, then we can only manipulate say the initial concentration, inlet concentration and the inlet flow rate, right? So depending on which, it will determine the residence time of those QD crystals. So I think they will affect, which size we can obtain in the end. But yeah, thank you.
Okay. We are a little bit, okay, there's one more.
Yes, as far as I know, in order to calculate the Monte Carlo simulation, we need to the number of particles modeling. How many particles do you use?
Oh, okay. So, is it particle like you mean particle of QDs or?
Particle of QDs. Yes.
Oh, okay. Particle of QDs are determined by experiments. I mean, so for example, like they kind of decide how many seed crystals will be injected into this tubular reactor. So we got the number from them, and then we did the calculations. Is that what you're?
Okay, we talk later.
Okay, sure. Thanks.
Thank you, Professor Guan. Let's thank again.